Hey everyone, this is Rebecca Oliver, and this is going to be the PowerPoint and video presentation on the answers to the Chapter 6 handout over hydrocarbons. So what's going to end up happening is that this will be made into a PowerPoint presentation. It'll also be made into a video so that you can pause it. And then I'm also going to put a PowerPoint up with no narration in case you just want to flip through the slides on your own. So here we are. Let's get started. All right, so here we have problem number 1. And the very first thing you want to do is you want to look at the molecule. And what you're looking for are the types of bonds between the carbons, you're looking for branches, and you're looking at the overall shape. These are the things that will determine the name of this molecule. Now in this molecule we have basically a straight line with no branching, and all the molecules are single bonds. So let's start by counting carbons. And you want to determine the longest chain, and since there's only one chain in this one, it's pretty straightforward. And we're going to count those carbons to determine the root. And it is going to be the root that gives us the basic name of our molecule. And here we have 8 carbons, and the root name for 8 is oct. Now next, we need to determine what type of bonds are present, as this will determine the ending of the name of our molecule, and all the bonds between the carbons in this case are single bonds, which makes this type of a molecule an alkane, and all alkanes have the ane ending. So, and it's because it's an alkane, there's no second or double or triple bonds, so there's no need for any sort of locator number. They're all single bonds. We don't have to worry about that. The next thing we would want to take a look at is if there's any branches, but there are no branches, so we can just move on. And with this, we have enough information to name this hydrocarbon, and it is simply octane. With problem number 2, we start by looking at the molecule. And we have basically a straight line with some branching, and all of the bonds are single bonds, so we've looked at it. Now let's get started. And we start by counting those carbons. And you always want to determine the longest chain, which means you may have to try a couple of different pathways, but even with the branches, this one's pretty straightforward. And we're going to count those carbons to determine the root name. And as we can see, there are 8 carbons, and that means we're going to have a root name of oct. Now next we need to determine the type of bonds that are present, as this will determine the ending of the name of our hydrocarbon. And if we look again, we can see all of the carbons are single bonds, which means that this is going to be an alkane. And all alkanes have that ane ending, so at this point we can say that we have an octane molecule. Now we're not done, because what about those branches? Well, we have a branch. And we have another branch. So we actually have 2 branches, one at carbon 2 and the other one at carbon 5. Now with branches, we need to let our reader know what is in the branch. That is, how many carbons are in the branch, and we need to let the reader know where the branches occur. The other thing about branches is that when they occur, you need to number the longest carbon chain in such a way as to give the first branch the lowest number possible. Now I've already done that for you in this problem, so here we have, like I said, branches coming off of carbons 2 and 3. And if we look at both of these branches, each one has only 1 carbon in it, and the root word for 1 carbon is meth, and because these are branches, they're going to get a YL ending, and they'll become methyl groups. And when you have repeats of a type of a branch, you also have to give it a numeric prefix. And in this case, we're going to have to give these a numeric prefix, which means 2. So to name these 2 branches, we would say 2,5-dimethyl. And with that, we have enough information to name this hydrocarbon, and its name would be 2,5-dimethyl octane. With problem number 3, we're going to start by looking at this molecule, and we can see it's not a straight line. So we need to do some careful looking on how we're going to number this one. One of the things we can see is that all the bonds are single and there's a branch. And with that, I think we can get started. So let's start by counting carbons. Now you always want to determine the longest chain, which may mean you have to try a couple of different pathways. And why do we even count carbons in the first place? To determine the root name. So here is the longest pathway. And if we number it, the best way to number it is going to be this way. And we can see that there are 6 carbons, and 6 carbons have the root of hex, so we're going to start with that. This has a root of hex. Now next we need to take a look at those bonds that we've already determined are all single bonds, and that means that this is going to be an alkane. And all alkanes have the same ending. So thus far we have a hexane. Now what about branches? Well, we have one, and it's right there. So now with branches, we need to make sure that we let our reader know what the branch is, like what's in it, how many carbons are in that branch, and we also need to let the reader know where the branches occur. The other thing about branches is that when they do occur, you need to make sure that you've numbered that longest carbon chain in such a way as to give the first branch the lowest number possible. Now I've already done that for you in this problem. So this branch is going to have occurred at carbon number 3, and it contains only 1 carbon in this branch, which means that it is a methyl group. Meth is the root word meaning 1 carbon, and because it's a branch, it gets the YL ending. Now there's only 1 branch, so we don't need to worry about a number prefix, so we could name this branch simply 3-methyl. And with that, we actually have enough information to name this hydrocarbon, and it is 3-methyl hexane. Now with any problem, including number 4, you got to start by looking at that molecule. Now this one's not exactly a straight line, so we're going to have to be careful how we look at this one. And if we just take a quick peek, we can see all the bonds are single bonds, and there's going to be some branches because this just has stuff sticking off everywhere. So let's start by counting the longest chain of carbons. And you're going to want to determine which is the longest chain, and you may have to try a couple of different pathways to get to it. And we need to ask ourselves, why is it that we count carbons? To determine the root name. So after doing some looking and counting, I've determined that this is the longest path. It could actually be another one, but this is the path that I'm going to use. And if we do the numbering, you're going to see how I number it. We can see that we have 7 carbons. And 7 carbons has the root of hept. Now next we need to determine the type of bonds that are present, as this will determine the ending of our hydrocarbon. And we can see that all of the bonds between carbons are single bonds, which means that this is an alkane. And all alkanes have the same ending, which is ane. And so thus far we can say that we have a heptane. Now what about these branches? Well, we have some branches. In fact, we have several branches. And with branches, we have 3 of them, we need to let our reader know what is in the branch, that is how many carbons are in the branch, and we need to let our reader know the number of where the branches occur in our carbon chain. So the other thing that we need to be mindful of is to number that longest carbon chain in such a way as to give the first branch the lowest number possible. I've already done that for you in this problem. And like I said, we can see that we have branches off of carbons 2 and 3 and 4. Now the branches at 2 and 3 have 1 carbon each, which means that they're going to be methyl groups. Meth is the root word for 1 carbon, and because it's a branch it gets that YL ending. And then there's also another branch at carbon 4, and it has 2 carbons. The root for 2 carbons is eth, and because this is a branch, it gets a YL ending as well, which means it's an ethyl group. Now because we have 2 methyl groups, we need to include a prefix denoting that there are repeating methyl groups, and that is going to be the prefix of di. And with the ethyl group, we don't have to worry about that because there's only 1 ethyl group. So when we have multiple groups like this, the other thing we have to be mindful of is how do we know which one to put first? Well, we do it alphabetically, and we include that numeric prefix as part of the name. So the dimethyls are going to come before the ethyl. So to name the branches, we would say that we have 2,3-dimethyl 4-ethyl. And with this, we have enough information to name this hydrocarbon, and it would be 2,3-dimethyl 4-ethyl heptane. All right, number 5. And the first thing you're going to do with any problem is you're going to look at that molecule. And by looking at this one, we can see that this is pretty much an exercise in naming branches. So we're going to have to be careful how we count that carbon chain. The other thing we notice is that we have all single bonds. So let's go ahead and get counting. Now, if we're going to count carbons in the longest chain, we need to figure out where that is first. And just kind of taking a quick look, we can pretty much determine that just straight across is going to be our longest chain. But we're going to have to number that chain in such a way that the branches have the lowest number possible. Actually, the starting branch has the lowest number possible. Now, if we were to number this chain from left to right, the first branch would occur at carbon number 3. But if we were to number this chain right to left, the first branch occurs at carbon 2. So that's how we're going to number our long carbon chain. And why do we count carbons in the first place? To determine the root name. And we have 8 carbons, which means that we're going to start off with the root of oct. And next we need to determine the type of bonds present to determine the ending of the name. And as we already determined, all of the bonds are going to be single bonds, which makes this an alkane. And all alkanes have that ane ending. So this far we have an octane molecule. Now what about branches? We know we have a few because we can see them right here being circled in purple. And yes, there are branches. We have 4 of them. And with all branches, we need to let our reader know what is in the branch, that is, how many carbons are in the branch, and we need to let the reader know where those branches occur. Now we have branches at carbons 2, 4, 5, and 6. Now the branches at 2, 4, and 6 have 1 carbon each, which makes them all methyl groups. And meth is the root word meaning 1 carbon, and because it's a branch, it gets that YL ending. And because we have 3 methyl groups, they're repeating groups, we're going to have to let our reader know that by giving this methyl a prefix, a numeric prefix of tri, which indicates 3. Now we also have a branch on carbon 5, and it has 2 carbons. The root for 2 carbons is eth, and because it is a branch, it gets that YL ending. And when listing the branches in the name, we need to alphabetize them, which includes that numeric prefix in the case of the methyl. So the branches, we would say, would be 5-ethyl, 2,4,6-trimethyl. And with that, we have enough information to name this hydrocarbon, and it is 5-ethyl, 2,4,6-trimethyl octane. Problem number 6. What's the first thing you're going to do? Well, you're going to look at that molecule and see what you got going on here. So let's see, we have some interesting things going on. We have a couple of branches and we have a double bond. So we've done our assessment. Let's get counting. Now when we have a double bond, we need to be sure to include it in the longest chain. Even if that means that by including it in that long chain, we can't get as long a chain as if we didn't include it. I hope that makes sense. So you have to include the double bond in the longest chain possible, even if that means by including it you end up getting not the longest chain possible. Furthermore, you have to number the carbons so that it gives that double bond the lowest number possible. Does that sound familiar? Well, it should, because this is the same thing you do for branches. So what about branches? Well, when you have both multi-bond and branches in a molecule, you're actually going to tailor the numbering of the long chain to suit the number of multi-bonds. And then you're going to just simply let the branches fall where they may. And why do we count carbons in the first place? To determine the root name. So let's go ahead and do that. So if we start by counting at on the left going to the right, that's going to allow us to put that double bond in the lowest carbon position possible. And we can see then that we have 7 carbons. 7 has the root name of hept. The next thing we need to take a peek at is the types of bonds, and we've already determined that there is a double bond, which means that this is going to be an alkene, and all alkenes have that ENE ending. And the other thing, when we have a multi-bond, like a double or a triple bond, we have to let the reader know where that occurs. And in this case, because of how we had to number this, this double bond is occurring between carbons 3 and 4. So we're going to assign it a locator number of 3. And we place that locator number between the root and the ending, and that's according to the IUPAC rules. That's what we have to do. So far what we have is hept 3-ene. Sometimes you'll see it written as 3-heptene. That's acceptable, but this is the official IUPAC methodology. So what's next? Well, that would be a branch or two. And we have a couple of branches, and they occur right here. So we have 2 branches, and they're both coming off of carbon number 5. Now, with branches, like bonds, we need to let our reader know what's in the branches as well as where those branches are located. Now we have 2 branches occurring at carbon number 5, and both of these branches have 1 carbon each, which means that they're both methyl groups. Meth is the root word meaning 1 carbon, and because it's a branch, we give it that YL ending. Because we have 2 methyl groups, we also need to remember to include that prefix of di, indicating that this is a repeating group. Now each branch gets its own locator number assigned to it, even if it's the same number. So to name the branches, we would say that we have a 5,5 dimethyl. So yeah, you got to repeat the 5, letting your reader know that both of those methyl groups are located on the 5th carbon. And with that, we have enough information to name this hydrocarbon, and it is 5,5 dimethyl hept 3-ene. All right, here we have problem number 7. And what's the first thing you're going to do? You're going to look at the molecule and see what's going on. First thing you might notice is that we have no branches, but we do have a double bond. And with that, we can get started. So we're going to count carbons. And when you count carbons with a double bond, you have to make sure, number 1, to include it in the longest chain. And since we only have 1 chain here, that's going to be pretty easy to do. But what's the next thing you need to remember when counting chains with double bonds? You have to number the carbons so that it gives that double bond the lowest number possible. And by the way, why do we count carbons in the first place? To determine the root of the name. So let's do that. So we can see here that we've got 6 carbons, and the root name for 6 is hex. And what about bonds? Well, we've already determined that there's a double bond, and the type of bond is going to give the ending to the name of our carbon, hydrocarbon. And even if we only have 1 double bond present, it's still going to be considered an alkane, and all alkanes will have that ENE ending. And because we have a double bond, we also need to let our reader know where that double bond is located. And here we can see that it's situated between the bonds of carbons 2 and 3. So it's going to get a locator number of 2. And where are we going to place that 2? IUPAC says that we have to place it between the root and the ending. So thus far we have hex 2-ene. Now there's no branches, so that's kind of easy. And with that, we have enough information to name this hydrocarbon, and yes, it is hex 2-ene. Here we have problem number 8. And what's the first thing you're going to do? You're going to look at the molecule. And you might notice that we don't have any branches, but we do have a double bond. And with that, we can get started. So when you have a double bond, you need to do what? You need to make sure, first of all, to include it in the longest chain, and since there's only one chain here, that's easy to do. But what is the other thing we need to remember when numbering chains with a double bond? You have to number the carbons so that it gives that double bond the lowest number possible. And by the way, why do we count carbons anyway? To determine the root name. So let's do that. Let's give this molecule a count. And we can see we've got 9 carbons, and that means our root name is going to be known, N-O-N. Now we've already determined there's a double bond here, and the type of bond present is going to determine the ending of the name. And even if there's only one double bond present, it's still considered an alkene, which means that this is going to have that ENE ending. And because it does have a multi-bond, we need to let the reader know where that bond is located. And in this case, it's situated between carbons 4 and 5. So it's going to get a locator number of 4. Now, where do we place that 4? Well, good old IUPAC says that we have to place it between the root and the ending. So at this point, we can say that we have known for ene. There's no branches, that's easy. So at this point, we have enough information to name this hydrocarbon, and it is known for ene. Now for problem number 9, the first thing we're going to do is look at the molecule. In this problem, we have a structure that actually forms a loop. So there's going to be a special prefix we're going to use for that. And we have a couple of branches off of this loop. And if we look, our loop has all single bonds, and that's going to dictate the naming of our molecule. And with that, we can get started. So when you have a closed loop of carbons, that is going to be your longest chain. Anything else is going to be considered a branch off of that longest chain. So to get our root, we're going to count the carbons in the loop. So let's start numbering these carbons. And you can see that we have 5 carbons in our loop, and that means our root name is going to be pent. Now we've already determined that all we have are single bonds, and that means that we've got an alkane, and all alkanes have that ANE ending. And there's one other thing at this point we need to take into consideration, and that's because our main carbon chain forms this closed loop, we must also convey that to the reader. And we do that by using a prefix called cyclo. So at this point, we have a cyclopentane. Now what about those branches? Well, we've got a couple of them, and if we take a look, we can see that here they are. They're circled in purple. There are 2 branches. They're coming off of carbons 1 and coming off of carbon number 3. Now, when you number the branches in a ring, just like with a long chain, you need to make sure that you've numbered that ring so that those branches have the lowest number possible. And that's why I numbered this ring the way that I did, starting with number 1 at a branch and then making sure that the next branch was at the next lowest possible number, which was 3. If we look at what we have in our branches, both branches have 2 carbons each. And that means that these are both going to be ethyl groups. And because they're repeating groups, they're going to get that prefix of di. So that's a little bit about our groups. And we can actually name these groups right now. We could say that we have a 1,3-diethyl. And I think with that, we have enough to name this hydrocarbon. And we would say that it is a 1,3-diethyl cyclopentane. Now for problem number 10, what is the first thing you're going to do? Well, I hope you said you're going to look at it, because that's the first thing you need to do. You need to see what you've got here. And the first thing I hope that pops off the page is that you have a double bond. So when you have a double bond, you need to make sure that you include it in the longest chain, even if that means you got to shorten the chain to get it in there. But I don't think that's going to be the case with this molecule. And ultimately, we're probably going to end up having a couple of branches because we have a lot of pokey outy things here. So with that, we can get counting. So when we have a double bond, we need to make sure that it gets included in the longest chain, and we need to number the carbons so that that double bond gets the lowest possible number. And why do we count carbons anyway? To determine the root name. Now in this molecule, there are a couple of correct ways to count the carbons, but this is the path that I'm choosing. It's random. I'm just choosing this path. It works out if you were to choose the other path, but I'm just choosing this one. And you can see that I've made sure to include that double bond. The other thing you'll notice about that double bond is that it is closest to the carbon at the top right. So we're going to start counting there. So that's going to be our starting point up there at the top right. And we can see that we've got 6 carbons in our long chain, and 6 has the root of hex. Now, that double bond is going to determine the ending of the name, and that makes this molecule an alkene, and all alkenes have that ENE ending. And the other thing about having an alkene is that we need to let the reader know where that double bond occurs. And we can see that it's located between the second and third carbons, or carbons 2 and 3. So it's going to get a locator number of 2. So at this point, we can say that we have a hex 2-ene. Now what about branches? We got some branches here. There we go. Yeah, in fact, we've got 2 branches. We have a branch off of carbon number 3 and the other one off of carbon number 4. And if we look at what we've got in these branches, they're both ethyl groups. Each one has 2 carbons in it. The root for 2 carbons is eth, and because they're branches, they get that YL ending. Hence the words ethyls. And because we have 2 of them, that means that they're repeating groups. And what do we do with repeating groups? We have to include a numeric prefix, and in this case, the prefix for di, which means 2. So we could name these branches 3,4-diethyl. And I think at this point, we have enough information to name this hydrocarbon, and it would be 3,4-diethyl hex 2-ene. Okay, here we are at problem number 11. And what's the first thing you're going to do? You're going to look at your molecule. You're going to see what you have. And among the things you notice are the number of bonds. What do we have here? Everything's a single bond. And do we have any branches? Yep, we do. So with that, those observations, we can get started. And we're going to start by counting. So you always want to make sure that you count your long chain first. Now, there are a couple of ways to count this, and they're both correct. But this is the way that I'm choosing to count this, the carbons in the long chain. And if we do that, we can see that we actually have 5 carbons in our long chain, and that would give us the root of pent. Now, we've already determined that there are all single bonds here, and that's going to make this an alkane, and all alkanes have that ANE ending. So at this point, we could say that we have a pentane. Now, what about branches? Well, we have a couple, and we have made sure to number our carbon chain so that these branches fall in the lowest numbering possible. So we have a branch off of carbon number 2, and we have another branch off of carbon number 3. Now, one branch has 1 carbon and the other has 2 carbons. The root name for 1 carbon is meth, and because it's a branch, we give it that YL ending. So the branch off of carbon number 2 is a methyl. Now for the carbon coming off of the branch coming off of carbon number 3, it has 2 carbons, and the root for 2 carbons is eth, and because it also is a branch, it gets that YL ending, making it an ethyl group. Now, do we need to have numeric prefixes for either one of these groups? Nope, we don't, because neither one of them is a repeating group. So we don't need to worry about that in this instance. But which group do we put first? Well, you might remember that we have to list these alphabetically, which means that in this instance, the ethyl is going to come before the methyl. So for these branches, we would say that we have a 3-ethyl, 2-methyl. And I think with that, we have enough information that we can name this hydrocarbon, and it would be 3-ethyl, 2-methyl pentane. Oh boy, here we go. Got problem number 12, and we're going to take a look at it, and I'm looking at it. And we can see that we have a closed structure. It's considered a ring. Even though it's square, it is considered a ring. And we can see that it has a double bond. Alrighty, so let's get started. So the first thing you always want to do is you want to count the number of carbons in your long chain, which in this case is the number of carbons in this ring or square ring. And we do this in order to determine the root name. And if we number it, I'm strategically numbering it. I'll address why I numbered it this way. We can see that we have 4 carbons and the root for 4 is bute. Now we've already determined that there's a double bond, and the thing we know about double bonds is that it puts that molecule in the classification of an alkene, and all alkenes have that ene ending. Even if it only has one double bond, we still call it an alkene. The other thing about alkenes is that when we have a double bond, we need to let the reader know where this occurs. So it becomes important that you number your longest chain in such a way as to give that double bond a low number. And if we look at this, you can see I numbered this in such a way so that that double bond falls between carbons 1 and 2. Yeah, so that's going to have the locator number of 1. Now, what's the other thing that we need to remember when we have a looped or a closed ring? We need to give it that special prefix that lets the reader know that we're dealing with a closed ring carbon. And that special prefix is cyclo. So at this point, we would say that we have a cyclobute-1-ene. And we don't have any branches, so we don't have to worry about that. And yeah, we've already pretty much named this hydrocarbon. So yeah, this is cyclobute-1-ene. Gotta love IUPAC. And here we have a cute little hydrocarbon. And how do we know it's cute? Because we're looking at it. And we can see that there's all single bonds and there's no branches. This should be pretty easy. So let's get started. So what do we want to do? We got to count those carbons. And we can see that we got a ring, even though it's a triangle. And so that's going to be our long chain. Our triangle ring is going to be our long chain. And honestly, no matter how we count them, we're going to have 3 carbons. And 3 carbons always has the root of prop. And we've already determined that all of these are single bonds. Yes, they are single bonds, which means that this is an alkane, and all alkanes have that ane ending. And there's something else about this that we're going to have to add to the name to let our reader know that it is a closed loop structure, and that is the word cyclo. And that's pretty much it, because we don't have any branches. And at this point, we've pretty much done everything we need to name this hydrocarbon. And yes, this is cyclopropane. And it's just so cute. So here we have number 14, and we can see that this is a ring structure, that it's closed. We can also see that there's some double bonds here and no branches. And with that, we can get started. So let's start by counting the carbons in this ring. And if we start counting here, we can see that we have 6 carbons, and the root word for 6 is hex. Now we've already determined that there are double bonds here, and that's going to make this molecule an alkene. And all alkenes have that ene ending. And when we have a double bond, we need to let the reader know where this is occurring. And in this case, we have 3 double bonds, which means I have carefully numbered our carbons so that one of those double bonds starts at carbon number 1 to ensure that we have the lowest number possible assigned to these double bonds. So we have double bonds occurring at carbons 1, 3, and 5. And the other thing is that because we have these repeating double bonds, we need to assign them a numeric prefix, which means they're going to get the number, the numeric prefix for 3, which would be tri. So this is going to be a triene. Because this is a ring structure, we have to convey that to the reader as well. So this molecule is going to get a special prefix, and that special prefix is the word cyclo. There's no branches, that's easy. And with this, we have enough information to name this hydrocarbon, and this would be cyclohexa 1,3,5 triene. Now, because of IUPAC being IUPAC, there's actually another name for this molecule, and it is simply called benzene. And this is actually the accepted name for this structure in the world of chemistry and in IUPAC. And it is named that for reasons I won't go into here, but if this was on an exam, this is what I'd want you to name it, cyclohexyl-1,3,5-triene, because that would demonstrate that you understood IUPAC's rules better than IUPAC understands their own rules. All right, so here we have number 15, and we have a molecule being represented by a skeletal stick model, and I know that because I'm looking at it. There's no branches, and there's a couple of double bonds. That's good. So we got enough information to get started, and we're going to start by counting. Now, when you have a double bond or two in your molecule, you have to count the, quote, longest chain to ensure that both of those are in the longest chain, even if that means you can't get as long a chain as possible without them in there. I'm not sure if I said that right, but anyway, you always have to include the double bonds in the longest chain possible, even if that means that you end up not getting the longest chain if you didn't include them. So this one's pretty straightforward because we've only got one chain, and here they are. They're right in the middle of it. The other thing you have to do is number them in such a way so that that double bond gets the lowest number as possible. And why do we count carbons? In order to determine the root name. Now in this molecule, there's only one way to count carbons to ensure that our double bond has a root name, and that is by starting from the left and going to the right. This will give that first double bond a carbon locator number 1 because it's located between carbons 1 and 2. That's pretty simple. Can't get any better than that. And there's a total of 5 carbons, which means that this will have the root of pent. Now, those double bonds are going to help us determine the ending name that makes this molecule an alkene, and all alkenes have the ene ending. And we're going to also have to let the reader know where those double bonds are located. And we've already determined that one bond is located between carbons 1 and 2, and we can see that the other double bond is located between carbons 3 and 4. So we're going to give the locator numbers of 1 and 3 to our double bonds. And because we have repeating bonds, we also have to include a numeric prefix noting 2, which is di. So yeah, this is going to be a diene. Specifically, a 1,3-diene. We don't have any branches, and so it makes this at the point where we can name this, and this is going to be penta 1,3-diene. Pretty simple. Now here we have number 16, and it looks like it could be complicated, but when you look at it and you break it down, you can kind of see it's actually pretty simple. There's 2 possible longest pathways, but they're all single bonds. And both of those pathways would be correct. So let's go ahead and get started with counting. This is the pathway that I'm going to choose, just because it's visually easy to look at. And if we number it, we can see that we have 5 carbons, and 5 has the root of pent. And if we look at all the bonds, we can see that they're all single bonds, which means that this is going to be an alkane. It's going to get that ane ending, as all alkanes have. So far we can say that we have a pentane. Now what about these branches? There are 2 branches coming off of carbon 3. And if we look at them, both of them have 2 carbons each. The root for 2 carbons is eth. And because these are branches, we're going to give them a special ending of YL, making both of these groups ethyls. Now they're repeating groups, which means that they get that special prefix for the number 2 of di. So yeah, we got to acknowledge both of those ethyls. Also for both groups, we have to give them each a locator number, even if that means that they're located on the same carbon. We have to let the reader know where each ethyl is located. So yeah, we would actually have to say 3 and 3. So our branches would be called 3,3-diethyl. And I believe with that we have enough information to name this hydrocarbon. And we would say that it is 3,3-diethyl pentane. Number 17 is also demonstrated with that skeletal stick model, and I know that because I'm looking at it. And we can see that it has a triple bond to the right of the chain, and there are 2 correct ways to number this chain. Either one is correct, but this is the pathway I'm going to choose. So the first thing we're going to do is count carbons. Now we could count from left to right, but that wouldn't put that triple bond in a low number position. So I'm actually going to count from right to left to ensure that that triple bond gets a low locator number. There are 8 carbons in this chain, which means that it has the root of oct. And we've already determined that there's a triple bond here, which makes this molecule an alkyne. And we've determined that that triple bond is going to occur between carbons 2 and 3, which means it's going to have a locator number of 2. So thus far we have an oct-2-ine. Now what about branches? Yep, we've got a branch right here coming off of carbon number 6. And this branch contains 2 carbons. And when you have 2 carbons, it has a root name of eth. And because it's a branch, it gets that YL ending, which means it's an ethyl, and it's going to get a locator number of 6. So our branch is 6-ethyl. And with that, we have enough information to name this hydrocarbon, and it is 6-ethyl oct-2-ine. All right, let's have a look at number 18 here, and we see all single bonds with some simple branches. It looks good, so let's get started. And there's an obvious long carbon chain here, but the question is, do we start numbering the carbons from the right or the left? Well, we always want to number the carbon to give our multi-bonds or branches the lowest carbon number possible. Now, to make this happen for this one, this molecule is going to be numbered from right to left because it'll put that first branch at the second carbon. And we can see that we have 10 carbons, which is going to give us the root of dec or deca. This kind of depends on how it flows off the tongue. And all the carbons are single bonds, which means that this molecule is an alkane. And all alkanes have that ane ending, and this one will as well. So thus far we could say that we have a decane. Yep, a decane. Now, we got a bunch of branches here, don't we? We sure do. So there are 3 branches, and they are coming off of carbons 2, 7, and 8. And each one of these branches has 1 carbon, and the root for 1 carbon is meth, and because they're branches, they get that special YL ending, making them methyl groups. So we've got 3 methyl groups occurring at carbons 2, 7, and 8. Now, because we have 3 methyl groups, that means that they're repeating groups, right? And they get that special numeric prefix in the name, and that prefix is going to be tri. So we could name our groups 2, 7, 8 trimethyl. And with that, we've got enough information to name this hydrocarbon, and it would be 2, 7, 8 trimethyl decane. All right, here's number 19, and we're going to take a look at it. And so I'm just looking at this, and there is a long chain here, and they're all single bonds, and let's get started. Yeah. So there are a couple of ways to count the longest carbon, but there is a best path, and the best path is right here. And the question is, do we start numbering this best path from the left or to the right? Well, you always want to number your longest carbon chain so that either multi-bonds or branches end up with the lowest carbon number. And to make it happen here, this molecule will be numbered from left to right. So if we start counting left to right, we can see that that's going to place that first branch at carbon number 2, and that our carbon chain has 5 carbons in it, which is going to give us the root of pent. Now we've already determined that these are all the bonds are single bonds, which means this molecule is an alkane. And all alkanes have that ane ending, and it's going to include this one as well. So thus far we could say that we have a pentane molecule. Now what about branches? We've got a couple of carbons with some branches off of them. And we have 3 branches coming off of 2 carbons. Carbons number 2 and carbon number 3. Now 2 of these branches contain 1 carbon each. The root for 1 carbon is meth, and because they're branches, they get that YL ending. So on carbons 2 and 3, we have methyl groups. And there is going to be two of them, which means that they're repeating groups. So we have to include that numeric prefix in their name, and the numeric prefix is going to be di. Also, we have another group coming off of carbon number 3, and this group has 2 carbons in it. The root for 2 carbons is F, and because it is a branch, it gets that YL ending. So for this group, the name is going to be ethyl. It gets a locator number of 3. So it's going to be a 3-ethyl. So to put all of this together, we would say, and remember these are going to be in alphabetical order, including the numeric prefix, this would be a 2,3-dimethyl 3-ethyl branch. And I think with all of that, we are ready to name this hydrocarbon, and this would be 2,3-dimethyl 3-ethyl pentane. All right, if we look at number 20, we can see that this is the same molecules we saw in 19, except that it has a double bond in the far right. And I'm going to attempt to work this 2 ways in order to get to its name, although we're going to see that one way is preferential. So let's get started. So we've already taken a look at it, and now let's count carbons. Now there's a couple of ways to get the longest carbon chain, and I'm going to count the chain so that it goes like this. This will give me 5 carbons. If I were to continue counting to the left, I would have 5 carbons, but we're going to name it this way. So we've got 5 carbons, and that's going to give us the root name of pent. Now, because we have a double bond, we always have to number our longest chain in such a way that we're giving that double bond the lowest number possible, and we've done that. And so we can see that the double bond is going to fall between carbons 1 and 2, and it's going to have that locator number of 1. So far we can say that we have a pent 1-ene. Now, what about branches? Yep, we have branches, and we have 2 of them coming off of carbon number 3. Now, one of those branches is methyl because it has 1 carbon. So the branch that is going down from number 3 is going to be a methyl group. But what about that chain that extends from number 3 to the left? Well, there's 3 carbons there, but it's not a chain of 3 carbons. They're branched. If it was a chain of 3 carbons, we could call it propyl, but it's not a chain of 3. So we can't call it that. And so basically, we've just stepped into some sort of a mess, haven't we? I'm sure there's some sort of an IUPAC rule for this, but for this course, that's not where we're going. That's a little bit more than we need to bite off in this course. So we're going to stop right here and see that we basically have just kind of come to the end of our understanding of the rules, and stop this process and see if there isn't a better way that we can number this carbon chain so that it makes a little bit more sense given what we know about IUPAC rules. So here's the same number. The same molecule, same number, but this time we're calling it version number 2. And this time I am going to number these carbons going from right to left straight across. And when we do that, we still have 5 carbons, and we're going to get that root name of pent. We've already determined that there is a double bond, and we've numbered our chain so that that double bond falls between carbons 1 and 2. So it's going to have that locator number of 1, and that's going to make this pent 1-ene. So far, so good. What about branches? Well, this time we've got branches occurring at numbers 3 and numbers 4. So carbons 3 and carbon 4 are going to have branches. So there are 3 branches coming off of 2 carbons. So if we look at the type of branches that we have, we can see that coming off of carbon 3 and carbon 4 are a couple of methyls. And then we can see coming off of carbon 3 is an ethyl. Because we have repeating methyl groups, we're going to have to give them a numeric prefix of di. And putting all of that together, we can name our branches as 3,4-dimethyl 3-ethyl. And with this, we have enough information to name the hydrocarbon. And our hydrocarbon is indeed 3,4-dimethyl 3-ethyl pent 1-ene. So this was an example of showing you what can happen if you choose a path that is not the right path. you get a little bit kind of in a quagmire of IUPAC naming. Um, Really, the bottom line is that you always want to pick the path that's going to give you the smallest branches possible. That's really what you want to do. And I think we got one more to go, and then we'll be done. So let's do it. And we have arrived at our final hydrocarbon. And as we have done with all of the others, we are going to look at it. And when we look at it, we can see we have a couple of double bonds as well as some branches. And it looks like we got a couple of repeating methyls and an ethyl. Okay, so let's get started with counting. Now, we need to determine the longest carbon chain, and we have to be sure to include both of those double bonds, which means there's only one way we can take, and we're going to number it just like this. And that means we've got 7 carbons, which means our root is going to be hept. Now, because we've already determined that we have double bonds, that's going to make this an alkene, which means we're going to have that ENE ending. And we also have to let our reader know where those double bonds are found. And they're found between carbons 1 and 2, as well as carbons 5 and 6, which means they get the locator numbers of 1 and 5. And because these are repeating bonds, they're also going to get that special numeric prefix of di. So if we put all of this together, so far we have hept 1,5-diene. And what about branches? Do we got branches? Oh yeah, we got branches. We got 3 branches. And our branches are located off of carbons 2, 3, and 4. Now if we look, we can see carbons 2 and 4 are where the methyl groups are, and these are repeating groups. We have an ethyl that's coming off of carbon number 3. And what do we do about those repeating groups? We got to make sure it has that number in front of it. And because there's 2 groups, it's going to get the number di. So if we put all of this together, we can say that for naming our branches, we would have a 2,4-dimethyl 3-ethyl. And with that, we have enough information to name this hydrocarbon, and it is indeed 2,4-dimethyl 3-ethyl hept 1,5-diene. Hallelujah, we are done. I sure hope you found that helpful. And I will see you in class. Thanks for watching.